Chapter 9, Section 4, Mechanisms of Plate Motions. Evidence for plate tectonics. Some of it came from earthquake patterns. Scientists found a close link between deep focus earthquakes and ocean trenches. The absence of deep focus earthquakes along the oceanic ridge system was shown to be consistent with this new theory of plate tectonics. Ocean drilling provided further evidence. This gave us the data on the ages of the seafloor sediment, and it confirmed what the seafloor spreading hypothesis had predicted. The youngest oceanic crust is at the ridge crest, and the oldest oceanic crust is at the continental margins. So that's saying that the youngest is right along that mid-ocean ridge, and the oldest crust is where the oceanic crust meets the continent. Causes of plate motion. Scientists generally agree that convection currents occurring in the mantle is the basic driving force for all plate motion. Convective flow is the continuous flow or motion of a fluid resulting from changes in temperature. So remember that the Earth's core is giving off heat constantly, and because the Earth is made up of different materials, they're going to heat in different manners. Some things will heat very evenly, some things will heat very quickly, and others will be slow. The hot, solid rock of the mantle behaved in a plastic way. That is, it can flow slowly over geologic times. So much like molten plastic would slowly ooze over, they're predicting that some of the solid rock in the mantle is doing the exact same thing. Mantle convection. Mantle plumes are masses of hotter than normal mantle material that are ascending or rising towards the surface, where they may lead to igneous activity. The heat sources for the mantle convection include energy released by radioactive isotopes in the mantle and heat from the core itself. The unequal distribution of heat within Earth causes the thermal convection in the mantle that ultimately drives plate motion. A mantle plume is a rising column of hot solid mantle rock at what we call a hot spot. The mantle plumes are masses of hotter than normal mantle material that are rising towards the surface, and they lead to igneous activities such as volcanoes or lava flows. Here we can see the diagram. The core is heating up the material surrounding it, and that heat's being transferred. And once in a while, there's a weak spot in the crust. And so that superheated mantle material will rise and create a hot spot. In this case, it's in the middle of the ocean. And as that plate is moving, it's leaving little dots of islands, that volcanic trail. On the side, we can see the descending oceanic plate. So this plate, this crust, it's the oldest of the ocean's crust. The newest would be here in the oceanic ridge. That oldest stuff is meeting the continental crust. It's subducting. It's coming back down into the mantle area where it's remelted, recycled, and it keeps cycling through. Hotspots are concentrations of heat in the mantle capable of producing magma, which is rising to the Earth's surface. The Pacific plate moves over one of these hotspots, and that's what produces the Hawaiian Islands. Hotspot evidence supports that the plates move over Earth's surface. So these smaller islands over here are older, whereas the big island of Hawaii is the newest, and it's constantly moving, it's adding to its material. That hotspot keeps feeding to it. I believe the Hawaiian Islands, the big volcano has been erupting consistently for the past 1.5 to 2 years right now. Here's another image. You can see that mantle plume spewing up from that hotspot, and that's the direction of the plate movement. In the process called whole mantle convection, rock rises from the lower mantle towards the top of the mantle, then sinks back down. This process takes millions of years. Think about a pot of boiling water. The sinking of the cold ocean lithosphere directly drives the motions of mantle convection through slab pull and ridge push. Some scientists think mantle plumes are involved in the upward flow of rock in the mantle. So Slab pull and ridge push are concepts that you're going to need to be familiar with. Slab pull is just this mechanism contributing to plate movement in which cold, dense oceanic crust is sinking into the mantle. And when it does that, it will pull the trailing lithosphere along. Think about like a slinky. Once it starts going down those stairs, it's going to pull the rest of it with it. The force of the gravity pulls old ocean lithosphere, which is relatively cold and dense, back down into the deep mantle where it can be remelted. Ridge push causes oceanic lithosphere to slide down the sides of the oceanic ridge under the pull of gravity. That stiff ocean lithosphere slides down the asthenosphere that is elevated near the mid-ocean ridges. Here we can see it's pushing here as it's rising and creating new. It's pushing, and over here it's pulling it under. Here's another diagram of slab pull and ridge push. We can see the core of the Earth where the heat's coming from. It's heating up the mantle. It's rising, creating that ridge. And this lithosphere is sliding over the asthenosphere into that trench where it's remelted. So slab pull is when it's sinking down at the trench, it's pulling that slab of oceanic crust with it. Here, you can see that ridge push. It's pushing from this side right here. So if this was the slinky, this is the front part of the slinky that you're pushing down the stairs. The push would be that initial shove that it would take to get it going. And then the convection currents in here are what's distributing the heat from the Earth's core. That volcanic chain, this one happens to be on a continental crust. So the Pacific Northwest would be an example of this with Mount St. Helens. As this goes down and it creates that friction, that added friction, helps to melt that rock again, creates these bubbles of hot magma that are rising and creating volcanoes all along that boundary or that border. So these are the mechanisms that help prove and explain why we have certain structures here on the Earth's surface. It explains how the Earth is changing, the features have changed, and how they will continue to do so in the future.